Okay, first part of the booklet up to now, we've been looking at basically that everything we did previous to this booklet was wrong. All the stuff we did studying waves, um, no, actually, waves have particle-like properties in some cases. Um, the next part of the booklet we'll look at, okay, well, if that's true, waves have particle-like properties sometimes. Do particles sometimes have wave-like properties? And where this came from was the de Broglie equation. We have already come across um, our equation that links the energy in a photon to its perceived frequency. Um, One of the most famous equations in science then is E equals mc squared, which deals with, well, we have already come across the conservation of energy. I'm sure in chemistry you've come across the conservation of mass. In fact, what we're told in physics eventually is you can't take those two things separately. They're all one of the same. And there's a link between mass and energy, and they're linked by Einstein's equation E equals mc squared, where c is the speed of light. What I want you to do is try and see if you can do what de Broglie did, um, linking those two equations to get an equation that links an object's momentum to its wavelength. So pause it now. He got a Nobel Prize for this. See if you can get a Nobel Prize. So if you pause it, try it yourself, and then hit play again. We'll see if you can get it right. Okay. The key thing to start off here is just let those two equations equal each other. So they both equal E. So therefore, mc squared must equal Planck's constant times frequency. But we needed a third equation here, really, which is that your wave equation, V equals F lambda, as we were told we want to link in wavelength. However, for a light wave, that is the speed of light. So we can rewrite that the frequency is c divided by lambda. Subbing this here in for frequency in our equation on the left hand side there gives us mc squared equals hc over lambda. So a c on that side and just one of the c's on this side will cancel out, and therefore we get that lambda equals h over mc. And from your work in module 1 you should know that a mass times a velocity is just a momentum. Okay, and we have this equation here. Now, what de Broglie took that to mean was that if we take Planck constant divided by a wavelength, we get a momentum. Therefore, photons, these little particles of light, which aren't actually balls at all, so I don't know why I'm drawing that, but we'll stick with it, must have a momentum associated with them, even though they don't have mass. Now, one way we can work out momentum is mass times velocity. You should think, therefore, if the mass of them is zero, the momentum should be zero. But we have another equation, which is just that it's Planck's constant divided by wavelength, and it should have an associated momentum with it. And it does, and we can measure it. And in fact, we use it in spaceships even. So we can build a little spaceship, and once it gets into space, it can unfold a big gold foil, essentially something like this, and it's something called the solar sail. And if this little particle hits into it and gets reflected, there's a change in momentum there, therefore that must impart a force or an impulse on our solar sail, and this can actually kind of propel the spacecraft across space in the same way that a yacht doesn't need an engine, it can just put out its sail and use the wind. And that was brilliant by de Broglie, being able to link all these things together and produce an equation that we could then test. However, Einstein was just brilliant at thinking outside the box. And what he said was, okay, well, if these little particles that don't have mass, these photons, can have a momentum, then can things with momentum, can everything that has momentum also have an associated wavelength? We don't mean we can measure something between two peaks. We mean it will behave like a wave under certain conditions and behave like a wave that has this wavelength. And he just rewrote the equation as lambda equals Planck's constant divided by momentum. And we'll look at how we can prove that Einstein was right.